invitation to talk here. So it's always nice to go back to, at least virtually, to Kaust and see familiar faces. So I do have 45 minutes, I guess, right?
Yes, 45 is definitely fine, yes.
Okay, good. Okay, so the title of my talk is combining noisy data and expert knowledge in a Bayesian calibration of a flow model under uncertainties. And it's in practice, it's an application to groundwater travel times of solute transport in the basin of the River Ticino. And it's a joint effort with Emily Baker, now back to the US, but previously a postdoc at Pavia, and a bunch of other guys from the Department of Mathematics and the Department of Civil Engineering of Pavia. So this is an application talk, so I expect a lot of practical stuff and maybe not so much new math, but let's see if I can make it interesting anyways. So let's start with some geography. We're talking northern Italy, and in particular, we're talking about the basin of the River Ticino. So if you look here on the right, in the zoomed area, this is the orange ellipse shows the northern Italy plains, the plains of the River Po, which is this river flowing from left to right here. It's the largest and longest river of Italy, and we're considering the plain in which the river flows, and in particular, we're considering the one of its affluent, the Ticino River. It's this river here in the red ellipse on the right. Maybe I should open the pointer. How do I? Here. Now you should see better. The Ticino River flows from the mountains into the Po River on the right here. And it's of interest because it's the river that flows through the city of Pavia. The city of Pavia is here in the blue star, which is a few kilometers south of Milan, southwest of Milan here. And what is the motivation of the work? The motivation is that in general, the northern Po plain is the leading producer of rice in Europe. Of course, it's not a production comparable to other big countries like China or India, but it's the largest production in Europe. And in particular, in the lower Ticino basin, that is, let's say, from the city of Pavia to the River Po, so this lower part of the red ellipse here, about 30% of the land consists of rice paddies that experience flood irrigation. So we have two questions. This work was indeed prepared during a joint project with a society that controls drinkable water in the basin of Ticino. So question one, how does the flood irrigation affect groundwater levels in the groundwater aquifer? And what is the residence time of groundwater and pollutants in the aquifer? Okay. So 29% of land again, so it's quite a lot. So this is a picture of the Po plains during flood irrigation. So you see it's definitely an important part of the landscape. Okay. This is another picture, and these rice paddies get flooded from May to September. So you can imagine that they do contribute a lot to the dynamics of the aquifer. So what we want to do in our mathematical terms is we want to do uncertainty quantification of travel times in the lower Ticino basin. So what we do is we have a model with two equations where we have the free boundary steady state Darcy model. As implemented in MODFLOW, we're using, I wouldn't say commercial software, but let's say we're using third-party software, so MODFLOW for Darcy free boundary. And then we do particle tracking by MODPATH, which is an add-on module of MODFLOW that essentially integrates the law of motion of particles. So there's no hyperbolic equation being solved here. And what do we do when it comes to uncertainty quantification? First, together with the colleagues in the engineering department, we individuated a bunch of parameters that we can consider uncertain, that we have to, I mean, we would like to have them fixed, but we have to consider them as uncertain. As you will see, it's 7 parameters, but the first thing that we do is a sensitivity analysis. Specifically, we use the Morris indices to discard the parameters that we can that are not influential, and we fix them to some reference value. Then we do inverse uncertainty quantification for the remaining parameters to get some, let's say, nominal value and some residual uncertainty. We decided to go down the road of Gaussian approximation of the posterior to make our life a bit easier. And then finally, the final goal is we actually do the forward UQ on travel times using the PDFs of the parameters that we determined at the inverse UQ stage. So what kind of data do we have? We have, to do the inverse uncertainty quantification, we have had data at 22 locations. We have 1 measure per location. All the measures are taken in different days, but all these measurements come from the period August-September 14. So that's why we want to do a steady state DRC model, because we have one data per measurement. So it wouldn't make sense to do transit model. And we have some expert knowledge on the, I wrote here flooded land. I should have said it's not exactly flooded land, it's more the amount of land where there are springs. This is a place where the piezometric head sometimes goes above land surface, and then water just comes out of the ground. Okay, so we know how much that area is, the area where we have springs. So what is the take-home message? I want to give you the conclusions in a sense before I even started. So reality is complicated. You will see there's a lot of details and things and discussions and approximations that we have to do. We cannot do UQ on everything. That would be just unrealistic. So we just have to take some decisions and then stick with them. Hopefully they are good enough. Software is what it is. We use MODFLOW, we use MODPATH. There's not much we can do about that. This will play a role in optimization, for instance. It's black box, so we don't have really a lot of flexibility here. Well, we use Python scripts to control MODFLOW and MODPATH. But again, the main point is there's no new math here. We just want to be able to go from A to Z. So from the description of the basin given by the geologists to some estimate of travel times, and we need to go there. It's not like it's optional. We want to get down there and want to go there in a, let's say, sensical way or informed way, let's say, right? And we found out that the engineers loved our UQ, even the basic one. So there's no really advanced UQ at stake here. There's computational Morris indices by sampling. The map point for the nominal values of the parameter is by even brute force optimization and plus Nelder-Mead, so simplex derivative-free optimization. We didn't do Markov-Chain Monte Carlo, we just did the Gaussian approximation of the posterior. But that's good enough, and the committants of this work, they were very positive about the results. So we think we did a good compromise between mathematical complexity and the results at the end of the day. And eventually the UQ is done, the forward UQ on travel times is done by simple Monte Carlo sampling. So let's get started, and I'm gonna spend a few moments on the model because you need to understand where the uncertain parameters are. So again, the pop plane are encircled in orange. The red ellipse is the Ticino River, and our domain is essentially the blue ellipse, so the southern part of the Ticino basin. It's in practice, it's this, let's say, rectangular domain here. The city of Milan is right here. The city of Pavia is right here. The Ticino River is, unfortunately, this graph is not the best, but the Ticino River is the blue thing going through the middle of the domain, and the Po River at the end is here. The other blue things are irrigation canals that are used by farmers to flood the rice fields, and the light blue dots are springs. You see that it's an important feature. There's a lot of springs, so the model has to deliver that these springs are actually there. And there's a lot of irrigation canals as well, the light blue ones. Step one, computational domain. So the computational domain, to do that, we get, it's a 3D domain. So we need to talk, once we have decided the borders, we have to talk thickness. So we have elevation data from we have a cartography map with 5-meter resolution, and we have some intuition of where the bottom of the aquifer is, thanks to some borehole data. It's not that many data, but we thought it was good enough to, let's say, do some linear interpolation of this data, and the thickness is the difference between the elevation and the aquifer base. Okay, remember that we're solving here the free surface Darcy, so we do not compute the flux in the unsaturated zone, so between the surface and the position of the boundary of within the saturated and unsaturated zone. What we compute is just the position of the boundary between the saturated and the unsaturated zone, but we don't compute the flux in the unsaturated zone. So to this end, the engineers thought it was good enough to use a mesh with 3 layers. And the first 2 layers are a bit thinner because we need to capture the position of the boundary between the saturated and the unsaturated zone. Then we have 600 times 700 cells in each layer. So in total, we have 6 times 10⁵ active grid cells. Active means wet, okay? And the grid has a resolution of 50 meters. And then the next step is permeability zones. We have previous knowledge from geologists that say that there's at least 3 different zones, 3 different geological units in the domain with 3 different permeabilities. Again, the river, the Ticino River is the blue thing, the Po River at the end is this other thing. And we have 3 zones, zone 1 in white, zone 2 in light gray, and zone 3 in dark gray. We know their ranges from previous explorations. We know that the permeabilities are sorted. So K1, the white zone, has the lowest permeability, and then comes K2, and then comes K3. Okay, so K3 is the most permeable unit. So when we do the inversion, we need to make sure that we land on something that respects this constraint. And these 3 parameters, the 3 permeabilities, are part of the UQ analysis. So we do a Morris analysis on them. If they are relevant, we actually do inversion on them. Otherwise, we will fix them. Okay. Then there's a lot of discussion on boundary conditions. The boundary conditions are crucial because it's where we encode the hydrological features of the thing. So it's where we actually impose rivers, canals, ditches, springs, and recharge of the aquifer from rain and recharge of the aquifer from rice fields. Remember that our goal is actually to understand how much the rice fields contribute to the overall dynamics of the aquifer. So in practice, we want to be sort of accurate about how we describe rice fields. So boundary conditions. On the base aquifer, there's a Neumann condition, no flow. Then there's 3 edges, west, east, and north edges, where we impose a Robin condition. Okay, a robbing condition where we impose where we know this. Okay, this is the equation of the robbing condition. The flux is equal to a constant times the difference between heads. The reference head is taken from a contour map of the groundwater head created by the region Lombardia. The constant is known, and what we don't know is the difference with so this HB, the extra head with respect to the reference value. This is something that we assume is between -2 and +2 meters, and this is again part of the UQ analysis. And this is the contour map, the far field map, if you want, that we use as a reference head here on the boundaries. Okay. So what we don't know here is the actual head on top of the reference head. We allow for our head to be ±2 meters from the reference. Then on the bottom here we have a constant head for a measurement of the river level. Then we need to impose also the presence of the river Ticino in the middle. The river Ticino, how we do that? So we have data of the level of the river here at the red dot at the city of, close to the city of Vigevano, and another measurement here close to the city of Pavia. So what we do, we use a third software, it's called HEC. It's another software that is used to compute flow in rivers. We solve the flow in the river using the data here and here to calibrate the results. Then we reinterpolate the results, and we use these reinterpolated levels as the clay boundaries. And actually, the head of the pressure on the river is this computed head plus a slack S, again ±1. So our base level of the river is the computed reinterpolated level plus ±1 meter. And again, this correction is part of the UQ analysis. And again, this is to make things a bit clearer. This is the level of the river at the first station. The level of the river at the second station is the blue. The level of the river at the confluence between the Ticino and the Po is the red. And these are the interpolated values that we use as base for the head along the river. Then we need to encode springs and ditches. We do that by another robbing condition. It's a similar robbing condition to the previous one, but now it's non-linear in the sense that we impose that water cannot enter in the domain from cells marked as springs. So on the far field, water can even enter or exit. On the surface, where we have these springs, the springs is a robbing condition with a max, so the water can exit but cannot enter the domain. What we don't know here is the discharge rate of the springs. It's something between 1 power -1 and 1 power 2 square meters per second, and again, it's part of the analysis, of the Q analysis. And there are 140 springs in the model. Then we need to encode the presence of rise fields. Rise fields are a Neumann condition where we impose that the flux is equal to some constant flux that we don't know again, and it's a part of the UQ analysis. This phenomenon is known to be important. Again, keep in mind that the rise fields are kept flooded from May to September, and the level is 5 to 10 centimeters of constant water there. So it's like a swamp in a sense. So it is without a sense, it is a swamp. So we need to be precise there. And incidentally, note that due to climate change, now many farmers are moving to dry rice cultivation because there's not enough water. So that is expected to have a major impact on the aquifer. So this is why we need to understand how much the rice paddies contribute to the level of the aquifer. And finally, we need to keep into account also the charge from rain. So there's another Neumann condition. So if you want, there's one Neumann equation, which is the sum of the two fluxes. There's flux from the rice fields and flux from the rain. And the contribution to the aquifer from the rain is the amount of water, the rain minus the runoff, the water that doesn't percolate in the groundwater but goes directly through on the river when it rains, and then the evaporation. So each of these three terms were estimated from this data. You see here we have data of daily temperature, daily humidity, daily radiation, daily wind speed. From these four information, you get the transpiration. Here, there's an information about rain. You take differences, essentially, a bit more sophisticated than that, but that's the philosophy underneath. And once you subtract the rain from the evaporation and the runoff, which was also estimated from some data, we get the residual flux. So to sum up, if I lost you, we have a Darcy model with 7 uncertain parameters, the 3 permeabilities. HB is a parameter that entered the Robin boundary condition on the north, east, and west edges. There is this parameter S, which is the slack on the river boundary condition. There's the R irrigation, which is the recharge from the rice fields with Neumann boundary condition, which is unknown. There's C, the discharge rate from the springs, which is another coefficient that enter another Robin boundary condition. So it's 3 permeabilities and 4 coefficients that enter boundary conditions. What we do sensitivity analysis on these 7 parameters to see which one are actually relevant and which one are not. So we do Morris sensitivity analysis. So to do that, we consider a few quantities of interest, not just one. The first quantity of interest that we consider is the root mean square error of the difference between the measurements of the heads and the prediction of the heads at the measuring wells. We take a look also at the percentage of heads above the land surface where a spring would occur. And then we consider the quantity of interest groundwater flux into the river, and then the actual head prediction at each measuring well. And then, given these 27 quantities of interest, we do Morris sensitivity on those. So how do you compute Morris indices? So you start from a random value of the parameters, and you compute the quantities of interest, and then for each parameter, you say you increase, starting from P, you increase, say, the first parameter of a certain delta. You get a new sample in the parameter space. You compute the new value of the quantity of interest. You take this difference, which is essentially a finite difference, a finite differences approximation of the gradient, or actually of the partial derivative of the quantity of interest with respect to the jth parameter, and you compute this elementary effect. Then you start over, so you perturb the second parameter, compute the finite difference with respect to that perturbation, then perturb the third, then perturb the fourth, and so on. So you get a sample of the partial derivatives of the quantities of interest. You repeat this procedure a bunch of times, so you get, let's say, R estimates of the partial derivatives of the quantities of interest with respect to each parameter, and then you average out everything in absolute value. So you essentially were trying to compute an average of the gradient of the quantities of interest with respect to the parameters. It's a sample-based average of the gradients. And what we get is, well, first of all, this generates a bunch of realization of the quantities of interest. So it's good to check whether, for instance, whether the actual data that you have lie in the range of the predicted values. So doing this, we have like a few hundred values of the quantities of interest, in particular, a few hundred values of the quantities of the heads, of the predicted values of the heads. The predicted values of the heads are the red lines, and the black dots are the measured wells. And we see that we are generating head values that are able to reproduce the measured wells. So we're happy. And these are the Morris indices of the 7 uncertain parameters as we increase the number of samples. By the time we get to 150 samples, we have confidently estimated the Morris sensitivity indices. And you can see that there's 3 parameters that matter the most. The red, which is the R irrigation, the green, which is the K in the zone 3, the closest to the river, and K1, the blue, the K permeability farthest from the zone, farthest from the river. The other 4 parameters are less important. This is a plot of the Morris sensitivity indices for the head at the wells. Again, the red is the R irrigation, K zone 1 is the blue, K zone 3 is the green, and those are the 3 most important parameters. All the other ones are less important. We also decide to keep the K zone 2 because there's at least 2 wells where K zone 2 plays an important parameters. So we decide to keep those 4 parameters, the 3 permeabilities and the R irrigation, and everything else instead we fix it because it's not enough influential in the predictions of the model. So now that we know that 4 out of those 7 parameters are actually what matters, we do Bayesian update, Bayesian inversion of those 4 parameters. Again, remember that we have 22 head data. We don't know the measurement error. And then we know that from expert knowledge, the area of the region where there's springs, where water naturally comes out of the ground, is around 1%, not more than 2%. So those 140 springs cover at most 2% of the land. So anything more than that is unacceptable. So how do we incorporate this information in our Bayesian inversion? We treat it as if it was another measurement. So let's say we claim that the prediction flow that let's say it's like having another measurement with an error, and the error is a Gaussian measurement, and it's tuned such that when you write the likelihood, the probability of exceeding 2% is essentially 0. So when you write the usual likelihood here, there's a typo here. I should have used, this is the likelihood of, this is the component of the part of the likelihood where you have the wells. This is the part of the likelihood where you have the prediction on the percentage of the flooded area. So HPAS is the percentage of head above surface. Head above surface. You see here there's head above surface predicted minus expected, so 1%. This term here becomes essentially 0 if you choose sigma, this S here, that here became a sigma, sorry about that. This part is essentially 0 if we tune S to be 0.33%. And after that, this is just a usual, you can just go around with the usual estimation of the maximization of the NLL. So you write the NLL and you maximize it to get the map, the maximum output, the nominal value of the parameters. There's only one catch here. The sigma H pass, it's known, whereas then we don't know the measurement error at the wells. So we cannot just, so what we do is we repeat the minimization of the NLL for a bunch of different values of sigma H, plausible values. For each value of sigma, we minimize negative log likelihood, and we get the corresponding value of the parameters. And then what we do is we chose the couple P sigma that yields the smallest NLL. And the results are these values. K zone 1 and K zone 2 are essentially identical, and K zone 3 correctly is larger, sorry. This is the rate of irrigation that we get, and the estimate of the measurement error at the west that we get is 3.6 meters, which is reasonable. How do we do this minimization? We don't do anything fancy. Using gradients-based optimization with MODFLOW is tricky because there's a lot of things that are out of our control, and you will stagnate into endless roaming around local minima. So what we do is we do a brute force on an initial grid. So we compute 6,300 parameters. We actually evaluate NLL there, which shows the best 3 results, and then we do derivative-free minimization, the Nelder minimization, starting from those 3 results. This is what we get, and we're happy enough. Notice that this is a bit tricky because I had to introduce this second term, this expert knowledge on the percentage of land that it gets flooded by springs, because if we didn't include that, if we were only doing the map estimate, trying to match the values of the heads, we would get really an unrealistic result where the 9% of the land would be springs, and we know that that is unrealistic. It has to be at most 2%. This is the modeled, the predicted head versus measured head, which reasonably okay. This is the distribution of the wells, and you see the error at each well, and it goes between -8% to +4% error. Let's say the committers of this work were happy enough with these quantities, and now we have to complete our Bayesian inversion. Instead of doing MCMC, we decided to keep it simple and just do the Gaussian approximation of the posterior, which only requires to estimate the covariance matrix of the posterior PDFs of the 4 parameters. So it's the usual formula. So the covariance matrix is the inverse of this H matrix. And the H matrix is an Hessian, and we approximate the Hessian in this way, where we see the Jacobians of the predictions of the Jacobian of the prediction of the model. So the Jacobian of the prediction of the heads, and the Jacobian of the prediction of the percentage of land with springs. One interesting side problem that we had is that to estimate Jacobians, you need to estimate gradients of the predictions of the model. That is done by finite differences. There was some work even in deciding what is a suitable value of the step that you need to do to compute finite differences. Again, due to, I wouldn't say problems, but let's say MODFLOW is not super responsive. So if you take finite differences, taking values of the results of MODFLOW with values of the parameters that are too close, MODFLOW just doesn't see any difference. Okay, so there's rounding probably or tolerances or whatever inside MODFLOW such that you cannot really go to very small values of the increment when you compute the finite differences. These are the marginals of our posterior PDFs. You see that K1 and K2 are really well captured. K3 is reasonably well captured. Our irrigation, we're still quite uncertain about it, but certainly it's better than having a uniform random distribution between 0 and the initial interval, let's say. So we're reasonably happy. But before going to the last step, now the last step would be to do forward UQ on the travel times using these 4 marginals as PDFs for the uncertainty quantification for the forward UQ. But before doing that, we took a little detour, and we tried to understand whether these results are meaningful and can we trust them? So what we did was we tried to do once more the Bayesian inversion with Gaussian approximation, but using synthetic data so we could understand whether our results made sense. So what we did was we chose some reference values for the 4 parameters. We ran MODFLOW to get the nominal heads and the nominal value of the floating surface. And then we added Gaussian noise to the heads. We ran the Bayesian inversion with those noise data. We repeated this operation 5 times for each level of noise. Then we increased the noise. And we see how often at each level of noise we reasonably recover the true values. Especially, we want to see what happens at values of sigma, which is either 3 or 4 meters, which is reasonably close to the experimentally assessed value of the noise. So what I mean is, by doing Bayesian inversion on the real data, we got a sigma H estimate of 3.6 meters. So we want to see what happens in synthetic data with 3 meters of noise and 4 meters of noise, to see whether in this regime there's we can be reasonably confident that our inversion is close enough to the reality. Okay, so short answer, yes. Results were decent, and now let me show you why I can be this sure. So first thing we did was let's try to we computed the ratio between the map and the exact value of the parameters. So you see here there's K1, K2, K3, and R irrigation. Here I will draw 1 dot for each synthetic inversion. So if the dots are, if the ratio between the map and the exact value is 1, we're perfectly nailing the value. So we want our dots to be clustered around this line of this 1. You see dots of 5 colors because it's the 6 colors, because it's the 6 levels of noise that we tried. For each color, there's 5 dots because we repeated the synthetic data inversion 5 times. And you want to see dots clustered around 1, but we're happy enough if we are off by a factor 2. So the dots don't have to go beyond this line, they would be 2, and below this line, there would be 1/2. So you see that, of course, the smallest the noise, the cluster, the better. So the noise, the results for noise 0.25, they're essentially stuck to 1. As you go to 3 or 4 meters, they are quite dispersed, but they are almost never beyond the factor 2. So let's say we're reasonably happy, especially for K2. We know that K2 is not that influential, so we cannot hope to really nail it, okay? Then we want to see the coefficient of variation. So we want to see whether we get the coefficient of variation is the ratio between the standard deviation and the predicted value. This has to be not above 2. Otherwise, when we generate values for the Monte Carlo sampling in the forward UQ, we would generate negative value of the coefficients, and this is unacceptable. And again, this is almost never the case. So we're reasonably happy about this. We also, here I plot the variance reduction. So the ratio between the posterior and the prior variance. You see that it's the posterior variance is almost always well below 1, this ratio. So we're actually doing mostly a good job in shrinking the variance of the parameters. These, I can skip these. These are the PDFs, the posterior PDFs. They are not perfect, but they're again good enough. So let me go finally to the final step, to the forward UQ on the travel times. So assuming or having convinced you that the Bayesian inversion give us reasonable values or reasonable PDFs for the parameters, we can now do forward UQ on them. Sorry? Did you say something?
No, nobody said anything. Please continue.
Okay. Okay. So, I mean, now that hopefully I convinced you that the posterior PDFs that we found with this procedure are good enough, we want to do forward UQ on travel times. So how do we do that? We place a particle in every 5th model cell. So in total, we're tracking 40,000 particles. We run the MODPATH module. Again, MODPATH doesn't solve an hyperbolic PDE as you would think. It simply integrates the law of motion of the particles using the flow computed by MODFLOW. So the velocity field of the particles is the Darcy flow, and you integrate the law of motion into over that velocity field. The velocity field that is being computed by running MODFLOW with the map values. And then we measure the time for the particles to get out of the Ticino, out from the domain into the river, okay? And this is the result. So this is the nominal value, because I'm using as velocity field the Darcy flow computed by the map value. This is the this is the nominal travel time, and this is the histogram of the nominal travel time. So let's say reasonably everything is said and done by 40 years of travel time. Now I have an echo. Can you switch off the microphone, please? Okay, thank you. So now this is, no, sorry, still echo. Okay, so where was I? Yeah, okay. So now this is the nominal histogram of travel times. Now what we have to do is to generate more histograms of travel times, computing travel times not for the nominal values of the parameter, but for values of the parameters that are being sampled from the posterior PDFs. Okay, so we generate 500 values of the uncertain parameters according to the posterior PDFs. We run MODPATH for each value of the parameters and for each particle. So we get 500 sets of 40,000 travel times. And we do statistics across the realization of travel times. So these are okay, so here in this plot, one line is a cumulative distribution of travel times, and you have 500 lines to show 500 cumulative distribution of travel times. So, for instance, if you cut this plot here at this level, from here you will see how does the 50 percentile travel time, so the median travel time spread across these simulations, these 500 realizations, okay? So varying varying the values of the parameters of the of the flow within their posterior uncertainties, the median travel time is around 4 years. And everything is, in any case, not less than 3, no more than 5. And if you instead cut this plot vertically here, you are fixing the travel time in years. So let's say 25 years. And this information is what is the percentage of particles that has travel time and less than 25 years across those 500 simulations. Well, let's say 88%, but in any case, less than 80, more than 76, less than 90. So let's say 80 to 90% of particles are out of the domain in less than 25 years. And this is an estimate which is robust to the nominal values of the parameters, okay? So this is a bit tricky to think of because we're doing UQ on histograms or UQ on statistical information. So it's statistics of statistics, okay? Of course, I could also do UQ of travel times for synthetic data, and unsurprisingly, the more noise you put on the data, the more the travel times are spread out. Nothing fancy, but I can just jump to the conclusion. So out of this long ride, what can we conclude from an engineering point of view or a geology point of view? We're pretty happy with the estimate of the coefficient of the recharge of the aquifer from the rice field irrigations. In particular, note that the nominal value that we found means that 90% of the total recharge in the summer months of the aquifer comes from rice fields. So what happens if farmers decide to move to dry cultivation of rice due to climate change? What happens is the aquifer will suffer, because at the moment the aquifer is essentially recharged by rice fields in summer. Then we were reasonably happy with the Gaussian approximation of the posterior PDF. And thanks to those posterior PDFs, we were able to estimate travel times. I have no idea personally what is a quick travel time and a slow travel time, but I was told that the result that we got was that the travel times are relatively quick. And we're decently good in estimating them because we have essentially an uncertainty of factor 2. So if you go back here, you will see that the median of the travel time is about 3 to 6. So there's a factor 2 of error. And if you repeat the same analysis for 90% travel times, you will see that the 90% of the particles are discharged between 25 to 50 years. Factor 2 estimate, and I was told this is reasonably quick as a travel time. Or if you want, 80 to 90% of the particles are discharged between 25 years. I'm done, and I leave you here with references. This is all of this is coming from these two papers here. And with that, I'll thank you for your attention, and I'm happy to answer any questions you might have.
Thank you, Lorenzo, for that very nice talk. Do we have any questions from the audience on this? We're just getting the mic for the question asker.
Yeah, I see that.
Okay, good.
Hi, Lorenzo.
Hello.
That was a very nice talk.
Thank you.
As an engineer myself, I greatly appreciate seeing UQ applied on search hard to model.
Very fun to do also. Yeah, thanks.
Yeah. My question is regarding the finding the map.
Yes.
I see that what you're doing is getting a grid, and then you pick some points, and then you use another mid to find the map, right? When you're doing this, yes, right? So when doing this, did you observe maybe multimodality of your posterior? Or
yes.
something?
Okay. So let me think. So first of all, yes. So what we did is we sampled those 4 parameters. We sampled them into 20 values for K1, 20 values for K3, 10 values for K2 because this is less influential, maybe 20 values for air irrigation. We get a Cartesian grid. We evaluate the NLL in those 6,300 points. Well, actually, we drop those points where the ordering of the K is not okay. So, but out of the values where we evaluate NLL, I don't remember, we compute the NLL, and then from the best 3 results, we did we ran the mid out starting from the best 3 points. I don't remember exactly, but I think we didn't find any multimodality because out of those 3 results were pretty far apart, and they landed anyways on the same on the same actual minimum. So I think I cannot claim with 100% confidence that there is no multimodality, but I'm pretty sure that we were careful enough to avoid local minima, let's say.
Okay, that's good, yeah. Because then if you had like this several evaluations of P, I imagine that of
Yes.
your NLL with this grid must be very expensive.
I was surprising. It was surprisingly not. I mean, one run of MODFLOW, the Emily, the girl that was running the thing, said that one run of MODFLOW was a few minutes. Could it be? I don't remember exactly. So it's quite expensive, but not the most expensive simulation I've ever seen, let's say.
Ah, okay, I see.
Yeah, so it was reasonably manageable, let's say.
Okay, thank you. That was it.
Thank you.
Alex, please. Sorry.
Hello, Lorenzo, Alexander here. Thank you for your
Alex.
talk. Question. Look, you identify unknown parameters.
Yes.
And if you're a little bit wrong with your parameters in Bayesian inversion, then your forecast is also not so accurate. Did you try to do direct forecast based on previous historical data without this intermediate step?
The forecast of what?
Oh, for example, on your last slide, you make conclusions that.
Okay, yeah. Okay, so you're right. If your nominal value, the map value is wrong, the prediction is wrong. Yes. That is why we tried the identifiability analysis, right? So we tried a few. So before concluding that our results were our map results were okay, we tried a few times with synthetic data with comparable noise, and we saw that most often were off, even at the levels of noise that we estimated were mostly off by less than a factor 2 from travel time for the parameters. And then so we thought it was good enough. And also, one other thing that I can say that I didn't mention earlier on is this. Where is it? Here. I skipped over this. Is this sentence here? If you run the MODFLOW at the nominal map values, you get some. You can compute the groundwater flux into the river, and that the number that we got out of there is comparable with the analysis that was done by another group on another river in the same area. So that was that gave us intuition that our map values were okay. The rice irrigation, the rice field, the irrigation contribution was also comparable to some previous studies. So the rice irrigation, the RIRIG that we got, this number here, is comparable with estimates provided by other different results, different procedures, and also the discharge rate from the springs was okay. So we have validation coming from expert opinion, different studies in the same region that give similar numbers, and validation coming from synthetic data. So running the posterior, running the Bayesian inversion with synthetic data with comparable noise gave us reasonable results. So we were happy. Does this answer your question?
Almost, but when you do Bayesian inversion and you identify 4 parameters, it could be that solution is not unique. Maybe in your settings it's unique, but when I optimize likelihood, usually you have multiple solutions which satisfy to your threshold.
Yes.
And then you do not know which one to take.
Yeah. Okay. But this comes. Okay. Then this comes to the previous question: how confident are we that our posterior is unimodal, right? And we were confident enough because of the optimization procedure, because let's say, evaluating the NLL starting the optimization from the 10 values of the parameters with the lowest negative log likelihood always ended in the same optimization. So we're reasonably confident that the posterior is unimodal.
Okay, thank you very much. I'm done.
Okay.
So one last question from Raul, please.
Oh, Lorenzo, very nice talk. Thank you very much.
Thank you, Raul. Thanks. Hi.
Hi. So quick question. Did you, maybe you mentioned that, but did you make some kind of verification analysis just to check what's the influence of the discretization? Can you play with this code and change the discretization parameters just to see that everything was robust with respect to that?
Yes and no. We did only, I mean, the only moment where we played with the mesh size was actually not a mesh size, was when we were computing derivatives of the, actually, no, sorry, I was confusing. No, we didn't do any test, or we didn't repeat analysis with different mesh sizes. The whole pipeline just took too long.
It's just a question.
Yeah,
it's just curiosity.
No, we didn't. I was I was a bit surprised. I was going through the papers and trying to get all the details, and I was surprised to when I found out that we were actually only using 3 layers in the vertical direction. I mean, the other two, I mean, 600 times 750 meter resolution over a few kilometers is good enough. 3 layers in vertical, it's not excellent. I don't remember why I was happy enough with having only 3 layers. Maybe, I don't know. Maybe I thought, okay, let's start with 3 and then maybe we will do more runs again with more layers in the vertical, but then eventually we didn't have time to do that. So I don't know whether these results are identical if we increase the mesh size. No.
Thank you very much. Yeah. Thank you very much, Lorenzo.
Welcome.
Okay, so
thanks.
I think let's thank the speaker once more. Thank you.
Thanks again. Thanks.